let's bring everything that we've figured out about these mass spring systems and LCR circuits together to come up with sort of the general case of what this second order constant coefficient kind of equation gives us. So here I have this second order constant coefficient homogeneous linear differential equation written sort of spring and mass style. But the first thing that I want to do here is divide everything by mass. So we get second derivative of y plus damping over mass times dy dt plus k over mass times y equals 0. And sort of it's a little clumsy to work out what the general solution to this sort of thing is with these coefficients being fractions like this. So sort of the traditional thing to do is name this coefficient, beta over m, name that 2 times lambda. You'll see why it's better to name it 2 in just a second. So 2 times lambda dy dt. So this is just defining a new variable lambda, really, or a new coefficient lambda. For this coefficient, we're going to give k over m a new name. We're going to call that omega squared. In the mass spring situation, you might remember that the sort of if there's no damping, the frequency of the angular speed of the oscillation is the square root of k over m. So here we're just reusing that name to define omega. So that makes this last term omega squared y equals 0. Okay, now when we write down the characteristic equation, we get m squared, and be careful, this is not mass, this m is just the variable for our characteristic equation, m squared plus 2 lambda m plus omega squared equals 0. And using the quadratic formula to find m, we get minus 2 lambda plus or minus the square root of 4 lambda squared minus 4 omega squared all over 2. And now you can see why it's kind of nice to have a 2 lambda here instead of just lambda. We can actually factor out a bunch of 2's and then simplify the whole mess, and we get minus lambda plus or minus the square root of lambda squared minus omega squared. Okay, now some things to notice about this is that if you go back and look at where lambda came from, right, lambda in the mass spring situation, it's beta over m, and in the circuit situation, it's resistance over inductance. But no matter where this comes from, lambda is always positive. It doesn't make sense to have negative mass or a negative damping coefficient or negative resistance or negative inductance. None of those things can be negative. They all have to be greater than or equal to 0. And so lambda itself is always positive. And that means that this part, minus lambda, is always negative. So that's something that we'll keep in mind. This term out in front always is negative. So we've seen there are 3 different cases. The first case is when the stuff in the square root is positive. So if lambda squared minus omega squared is positive, that's the overdamped case. So in that case, you get 2 values for m, and they're both real. They're distinct and real, so they're different real numbers. And in this case, your solution looks like some constant times e to the m1 m1t plus some other constant times e to the m2t. Okay, but actually we can say a little bit more than just this, because if you look back at the roots of our characteristic equation, minus lambda, so this part is negative, plus or minus the square root of lambda squared plus omega squared. So this is shorthand for two different values, right? One value is minus lambda minus the square root of lambda squared minus omega squared. This should be a minus right here. Okay, so for this first value, so we could call this m1, I guess, this root of the characteristic equation is definitely negative. There's no question, because lambda itself is positive, so minus lambda is negative, and this square root is positive, and it has a negative in front of it. So this stuff is all negative, right? So this first exponential term, this is decaying. What about the second exponential term? So the second root of the characteristic equation in this distinct real root case is minus lambda plus the square root of lambda squared minus omega squared. And here we have to think a little harder, because here we have a negative plus a positive. And so this might come out to be positive. So what we need to do is compare the relative sizes of minus lambda and plus square root lambda squared minus omega squared. But this stuff inside the square root, this is less than lambda squared, right? We have lambda squared minus omega squared. Omega squared is positive, so lambda squared minus omega squared is less than lambda squared. And so when you take the square root of lambda squared minus omega squared, that's less than lambda. And so that means that when you do this, when you have minus lambda plus this square root, it's the minus lambda that wins. So minus lambda is more negative than this square root is positive, and that means that when you add these together, you get something negative. So if we go back and look at this solution up here, this second term, it also is always exponential decay. This kind of makes sense because remember, what we were modeling in this situation is a mass on a spring. It would be very weird if you could choose a certain size mass and a certain spring and get exponential growth in the position of the mass. That means if you chose your setup just right and then gave it a tap, the mass would fly off to infinity. But that's not very realistic. And indeed, we're seeing that that can't happen in this situation. So it's kind of a relief that these both turn out to be exponential decay. You might wonder what happened to the exponential growth situation. What about this situation prevents exponential growth from happening? Well, if you look way up at the top, it's because lambda has to be greater than 0, right? To get exponential growth, you have to have some of these constants being negative, but none of them can be negative in the physical situation because we're dealing with actual masses and springs or actual resistors and inductors. So it's the physical constraints on the system, not the mathematical constraints, that prevent there from being exponential growth. Okay, so all of this was the overdamped situation. So now let's look at the second situation when lambda squared minus omega squared is exactly equal to 0. This is the critically damped. Situation. And in that case, right, there's only one root to the, in the critically damped situation, right, this square root part is actually 0, and so the only root for the characteristic equation is minus lambda, and it's a repeated root, it's real, and it has to be negative, because remember with lambda it has to be positive. And so in this situation, your solution looks like some constant times e to the minus lambda t plus some other constant times t e to the minus lambda t. And again, we get exponential decay, which makes sense. You can't get exponential growth because that means your mass would fly off to infinity, and we've seen that's impossible. Okay, so that's the critically damped situation. The remaining situation is when lambda squared minus omega squared is less than 0. And in this case, this is underdamped. And this is when we get oscillation. So if lambda squared minus omega squared is negative, that means omega squared minus lambda squared is positive. Right? So rewriting the roots of our characteristic equation, we get minus lambda plus or minus the square root of, so I'm going to write this stuff in the square root as omega squared minus lambda squared times minus 1. So that's the same as this stuff up here. So that's minus lambda plus or minus the square root of omega squared minus lambda squared times I. So our solutions in this case are e to the minus lambda t times some constant times sine of this angular speed, so square root omega squared minus lambda squared times t, plus some other constant times cosine of square root omega squared minus lambda squared times t. Okay. Since lambda is always positive, this exponential term in the front is always decay, never exponential growth. So in this oscillating situation, you do always get sinusoidal oscillation, but with an exponentially decaying amplitude like this. Notice that the angular speed of this oscillation is not quite the same as the undamped case. With no damping, the angular speed of the oscillation was just omega. But with damping, the angular speed is the square root of omega squared minus lambda squared. And remember, lambda has to be positive, so this speed is actually a little bit less than the so-called natural angular speed, which is omega. So it turns out damping slows down the oscillation a little bit, in addition to making the amplitude decay.